Okay, class. So we've talked about basic microstructures in ferrous alloy systems. We've discussed a little bit about heat treatments using the IT diagrams and the basic microstructures you can kind of identify from phase diagrams based on composition and temperature. So now we're going to be looking at manufacturing processes. So the difference between a forge and a cast product, you can identify through the macrostructure. So in the forming process, which is your wrought process, you typically can see flow lines of the grain structure, as seen in the image on the top left. So in this image, you can see a directionality of the material in this orientation, and then it forms and it kind of contours the head of this bolt or screw, whatever this material tends to be. So that was forged. When you're looking at a cast product like what you see in the bottom left corner, you see more of a directionality of the grain growth in terms of the columnar grain structure. So around the edges of this casting are very small equiax grains, because those would have been the first to nucleate and then solidify. And then the core of the material would have solidified at a slower rate. And that's why you end up with these columnar grains kind of growing inward. And depending on that cooling rate, you'll end up with either very large equiax grains in the center, or you can end up with small ones. Typically, they're going to be larger in the center because it stayed at temperature for a longer period of time, versus what you would originally observe at the edges. So when we're looking at processes, a hot form process is typically the deformation or hot working of a metal above its recrystallization temperature. Since all materials have different melting temperatures, you have to look at which material you're working with. And when you're deforming it, if you take 40% of the absolute melting temperature and form it above that, then you would be considered hot working. Typically, your hot work structures will exhibit equiax grain structures, but there will be evidence of banding or some other directionality of other constituents, such as inclusions. Residual stresses in this case are minimized, but they're not 100% eliminated. Some examples of what a hot formed microstructure looks like. This particular one here is of a flange that's consisted of banded perlite. You guys have had to do some definitions. So you see this banded structure where it looks like the perlite is running left to right, but when you look at the ferrite grain structure, the ferrite grains are equiaxed. If this was a cold work structure, then the entire microstructure would be elongated in the left to right orientation. This is a little description of how you could identify the microstructure itself. So in text, in a report, you would say the representative microstructure, because remember, when we're taking images, we have to identify the representative microstructure. So in this case, this one is the representative microstructure for the subject flange, consisting of banded perlite in a pro-eutectoid ferrite matrix, which is indicative of a hot forming process. So you're mentioning that it's a banded perlite structure in a pro-eutectoid ferrite matrix. Pro-eutectoid ferrite forms when you are a hypo-eutectoid steel. So this particular type of steel, I think the carbon content was around 0.3 weight%. So that is to the left of the eutectoid transformation. And upon solidification, proeutectoid ferrite will form first. The remaining amount of austenite will then transform to pearlite during the eutectoid transformation. A cold form process is during the deformation or cold working is occurring below the recrystallization temperature. So any deformation you're practically doing to a metal at room temperature, you are cold forming, deforming the metal. Once again, it's going to also depend on what your material is. If you take a hammer to steel at room temperature, then you're cold forming. There, you take a hammer to tin or lead at room temperature, and you would be hot working it. So once again, if you want to identify if you're hot or cold working your material, you'll just have to take 40% of the absolute melting temperature and see whether or not the temperature that you're forming at is above or below that. So typically, you'll see deformed or elongated grain structures with a considerable amount of slip, which are normal to see in body-centered cubic or face-centered cubic metals, or mechanical twinning in HCP metals. In the case of the microstructure, the residual stresses in this case are going to be very high due to the amount of dislocations that have now been introduced into the system, therefore increasing the dislocation density. So some examples of a cold form process. So once again, this is going to be the representative microstructure for a subject component consisting of intermetallic inclusions in a ferrite matrix. So our ferrite grain structure in this top right image, these are all at 100x magnification, would be equiaxed. These dark features that you see that tend to be running in the left and right orientation would be your intermetallic inclusions. Your intermetallic inclusions, I had mentioned before, would be like manganese sulfide. You could have oxides. Anyway, these are forming. These look like they're formed in the left and right orientation. Now, if we were, this has 0% reduction to it. Now, if we were to deform the structure by 40% of its original thickness, now you're seeing a structure that looks a little bit more elongated or pancaked. And I'm going to zoom in here real quick just to show that when you look in this grain right here, you can kind of see these dark features. Okay, same with this one here. And these dark features are oriented the same. Those are that's evidence of your slip lines that are now starting to become visible due to the amount of dislocation or deformation you're forming. So the dislocations are now forming along those slip lines. Okay, because remember, each one of these grains is its own crystal. That's why this is a polycrystalline material. So they're all going to be oriented differently, giving you these grain boundaries. So in this particular case here, the slip planes happen to be oriented, I don't know, just for the sake of the conversation, at about a 45-degree angle if you're looking at this being perfect 180. So now if we deform the structure even further, now you're going to see, you know, if this was one grain, now you can see a lot of these darker features in here. So the slip lines are becoming more pronounced, very much more noticeable compared to what we saw or what we did not see in an equiax grain structure here. Okay, so those are some of the telltale signs that you have a cold worked or cold formed process. Some of these processes for forming operations, so you have forging. So essentially that's the mechanical deformation of a metal. You do have open and closed forge setups. What's illustrated here is a closed forging. If it was an open forge, you can essentially you're forming the material between two plates instead of it being a design like this, okay? So this is a closed forge, meaning everything's going to be confined within a space. This is how metal billets are shaped into their final form by either pressing down or by hammering into their final cavities. This can be done hot or cold. It's easier if it's done cold. I'm sorry, take that back. It's going to be easier if it's done hot because the metal is more suited to be formed. Forming operations in terms of rolling. So you have two rollers that will reduce the cross-sectional area. So the metal goes into these rollers hot, and right after they flow through the rolls, the water then cools the material. So once again, this can be done hot or cold. If it's done cold, you can actually heat up the metal because of the amount of deformation you're creating into the material itself. If it's done hot, that's why you add the water cooling process. For better surface finishes, typically things are done cold. So you can do a couple hot passes, and then your final rolling process will then be conducted cold. You're not completely deforming the microstructure, but you are essentially making a better surface finish for dimensional purposes. During forming operations of an extrusion process, extrusion is going to be conducted with a ram. So you have this very hot billet, and this ram will then push this billet through a die, extruding your product. And that is where you are able to get different shapes than you would a rolling process. So this is going to take the shape of the hole. So if you wanted your metal to come out looking like a star or hexagonal, then that would be one of the ways that you can end up with that type of configuration. The last one we'll talk about is a drawing die. So in this case here, the force, you are pulling instead of pushing the material through the die, and depending on your angle of entry will kind of determine your the amount of forming that occurs. So the reason why you end up with an equiaxed grain structure during a hot forming process, probably better if I go back to the rolling, is in this particular instance, your grain structure over here should be equiaxed. Okay, it's going to be equiaxed, nice. Okay, then when it comes down and it becomes it goes into the smaller cross-sectional area, the grains are automatically deformed. Okay, and they're going to be deformed in how this material is being smashed together. But because of the heat being above the recrystallization temperature, the grains right at about this point will become smaller but equiaxed. Okay, so these are all going to be equiaxed grains here. So right at this moment, you end up with something called dynamic recrystallization. So the moment the grains are deformed, you're almost skipping that step of recovery and going straight into recrystallization. And that's why you end up shooting it with the water right here, is to then stop the grains from growing. And so you end up with a finer grained structure. So your mechanical properties will then be higher for strength, hardness, and things of that nature. If this was a cold forming process, then you're going to end up looking at elongated grains from this moment on this way. They're just going to be pancaked, elongated grains, and that would be your cold form process. If you were looking at producing then an equiax grain structure to relieve, for one, the residual stresses that have been implemented by your cold form process, then that means this piece will then go into an annealing process. So it's a completely separate process that occurs at a different location than the rolling mill per se. So looking at the grain structure here, this is definitely not a forged or cold worked product. This is now going to be a casting. And I start off with a white cast iron just to show that a lot of shrinkage porosity, okay, which is identified as all these dark regions here. All of this is where there was an inadequate amount of metal to fill those voids to create one solid piece. So you end up with a bunch of shrinkage in between the dendritic structure. Okay, so I was hoping that this image would identify what a dendritic structure looks like. And so if you make a fist and you look at how your fingers, your knuckles look, that is almost what a dendritic structure looks like. Okay, so looking at your fist, the areas in between your knuckles would be your interdendritic location. Okay, your fingers themselves would be your dendritic structure. So the reason why we ended up with a lot of shrinkage cavities in this particular casting, it's just the lack of molten metal during the pouring process. So if you did not pour enough metal into the process, or if your metal started to solidify too quickly, not allowing further metal to penetrate into your cavity, then this is where you would end up with a lot of shrinkage. So once again, this is a two-dimensional aspect, right? Because we're looking at this through a cross section, not 3 dimensions, the way we would see in an SEM. Here's also a more complete casting, I guess you can say. Once again, so this right here is going to be a representative microstructure of a white cast iron, and it's a dendritic grain structure. Okay, so these are your all the white regions. Okay, this forms martensite based on the heat treatment it went through, but your white regions that you see here and here, okay, those are that's your dendritic structure. So your carbides are interdendritic, which means those carbides are sitting right here, okay, and they're going to be eutectic carbides, just based on the phase diagram. It's got to cross the eutectic transformation line. So your eutectic carbides are sitting in interdendritic locations. Okay, this was colored etched just to help bring out the color of the carbides, because typically when you etch, carbides do not bring out a color. Typically they're either pink or a slight pink color. So if these were slightly pink in color and not dark to bring out the contrast, it'd be kind of hard to determine what your microstructure would look like. Once again, you do have shrinkage porosity in this particular photograph, just because the dark regions also interdendritic. That would be the last portion to solidify. We all know that metal shrinks when it solidifies. So once again, if there was not enough metal to fill the void space or the volume during the solidification process, then you end up with shrinkage cavities. And your shrinkage cavities will always be in the interdendritic spacing. Looking at a sand casting. So how do we get these cast products? Well, this here is a sand cast, and this is what we actually perform in our foundry. So you end up with your design, whatever you want, your mold cavity, and you're going to have a couple areas that you need to have in order to pour the molten metal into. For one, you need a gas vent. The gas vent helps during the solidification process, help get any of the gases out that could be formed, therefore causing gas porosity in your castings. But your pouring cup is where all of your molten metal goes into. So all your molten metal comes into here, and it fills this entire cavity, and then you have this region called a riser. So you're going to continuously pour molten metal, and your riser sits higher because once your cavity is filled right here, your riser should fill second. So as your cavity starts to solidify and shrink, it'll pull some more of the liquid metal out of your riser into the runner into your mold cavity, therefore completing your casting. This is a very cheap and easy way to cast molten metal. If you haven't had an opportunity to get into the foundry and cast products, this is a really cool activity to do. Then you have a die cast. So in a die cast, it's different than a sand cast because you will have a die fixture that is only used to make those particular parts. The one area over here on the left is the movable. So this area can be removed while everything else here is fixed. And the way this particular piece works is when you're ready to cast a component, you would put the movable half, mate it up to the fixed die, and you have these ejector pins. So what ends up happening is when you have them butted together, you form your cavity. Very similar to what we saw in the sand cast, but this one is you pour all of your molten metal into this chamber, and then using a plunger, you push that material into your cavity. So with it being forced in, it's more likely that you will not form shrinkage cavities and such, because you'll always have a pressure pushing the molten metal into the cavity until the whole thing solidifies. The only problem is you have to wait for it to completely solidify in order for you to then remove this piece, and then these ejector pins will then push your portion out, and then you'll just cut those off later. The die cast components are nice because they do mold up close to the tolerances of the design that you're looking for, and it has a nice smooth surface because the molds themselves or the dies are made out of metal, so the surface is also going to be nice and smooth. Sand, you'll have a more rough texture to it, and you could even encapsulate chunks of sand if the mold was not set correctly prior to the casting process. A continuous cast process or strand casting. So you have a ladle that sits above the entire process, and this is where the molten steel gets poured, and it will then be transferred to a tun dish, and that tun dish will slowly allow that molten metal to vertically be dropped down, almost like it's gravity fed. And these support rolls here and spray cooling will then form a slight casing of solidified metal around molten metal. Okay, so just like the coloration of this illustration, the molten metal is going to be orange. Okay, this golden color, and you can see right at around the second or third roll that is also assisted with spray cooling, it forms that casing encapsulating molten metal on the in the midsection of this casting. So as it moves further and further down, by the time it gets to this region of where they call it metallurgical length, the last portion of the molten metal solidifies in the very center, and then it's still hot, and then it gets cut by a torch. Therefore, now you have a continuous slab. The nice thing about this is it increases your production versus your traditional cast methods, where you have a ladle of molten metal, you pour the entire ladle of molten metal out into a casting, then you take the ladle back and start the whole process of remelting again. So during that process, each cast can be different versus the continuous cast process. Your molten steel, they don't allow this to completely empty. They are keeping the chemistry consistent, then pouring a little bit into a tun dish, keep the metallurgy here consistent, pour it into the tun dish, and you end up with a more continuous slab of material. So looking at the casting, looking at difference in microstructures for casting versus forgings, also hot formed versus cold formed materials, you should be able to easily distinguish now the differences between a casting, hot forge, or cold worked component. Once again, review your materials over ferrous alloys. Quiz due March 28th at the end of the day. Your assignment was due today by the end of the day. Exam 2 is postponed till April 9th. So continue covering anything on microscopy and the ferrous alloy systems for microstructures, heat treatment, and manufacturing. These will be covered on the second exam, and I will use Thursday afternoon to review any of the material that I covered on these presentations if you want to sign in and ask any questions. Thank you for your time. Have a good day.